All right, we now have, this is Physics 214 tutorial. For those of you and for the people watching at home, tutorial is a time where we can actually take a little bit more of a relaxed, pursuit of getting answers and stuff. It's definitely a time where if you have questions, that requires an answer other than yes or no with a little bit more detail, now is the perfect time to do it. Typically what we do is we just run through problems, solve them. It's only 10% of your final grade. I would prefer that homework not be worth anything for your final grade, but I also know that you wouldn't do it then, and then it would be the end of civilization. So I open the floor up to questions. Which ones do you guys want to work on? What? All of them. You know, the previous class, those 213 students actually had the courtesy of going, they started not with number 1 and then with number 2. They went they pulled a con a little bit and they went number 5, number 7, number 1, number 3, and eventually we just did the whole thing. So for what I'm gonna do is, just for the sake of saving time, because it is Friday afternoon, I won't do all of the vector problems. I'm gonna do one by breaking down, I'll break down A and C, and then I will do this one. So the first thing I'm going to do is break down the E field vector for A, which is 4 newtons per coulomb at 45 degrees, and C vector, which is 3 newtons per coulomb at 280 degrees. And then what I'm going to do is I'm effectively going to add these together in a special way. So A, by its theta being between 0 and 90 degrees, is a first quadrant vector. So that length is 4. That is 45 degrees. It's a first quadrant vector, so its reference angle is the absolute angle. This is the magnitude of A in the y and the magnitude of A in the x. And sometimes, actually, let me just be nice about it right now. AY, AX are how I typically use, when I'm dealing with vectors, I use lowercase for magnitude. AX is A cosine theta, and AY is A sine theta. Remember SOHCAHTOA from your trig days. So A is 4, the reference angle is 45. The fun thing about all of this is that cosine of 45 and sine of 45 is the same number. So in both cases, AX 2.828 and AY is 2.828. That means as a component vector, A, which is a first quadrant vector, is positive 2.828 x hat plus 2.828 y hat, close, newtons per coulomb. So that's the conversion of a component vector, or a polar to component for a first quadrant vector. C is a little bit different. C is a fourth quadrant vector. Fourth quadrant vectors are drawn like this. For those of you who are new, I always draw my x component first and then my y. That is my c, or 3. This is cx lowercase, cy lowercase. And the 280 degrees is that. That is the absolute angle of C. So the reference angle for C is 360 minus theta A, or 360 minus 280, or 80 degrees. Once again, we have to break down these into components. Magnitude Cx, C cosine theta reference, or 3 cosine of 80. So the magnitude of the C component (0.521) CY, C sine reference angle, or 3 sine 80, or 2.954. Now those are the magnitudes, and because it's a fourth quadrant vector, you know that the x component will be positive and the y component will be negative. So the C vector is 0.521 x hat minus 2.954 y hat newtons per coulomb. So that's the first for the first problem. You do the same thing for number 2. Number 2 is second quadrant, so it has its own little things that you need to remember. Now, for the second bullet of number 2, I have to sum up C minus 2 times A. So the C vector is simply 0.521 x hat minus 2.954 y hat. The A vector is 2.828 x hat plus 2.828 y hat. But if it's negative 2a, you multiply both components by 2 and toss in a negative sign. You just take that negative 2 and let it go through it. So 2.828 times 2, negative 5.656 x hat minus 5.656 y hat, and that is the value of negative 2a. Now we add them together. Effectively, what I'm doing is C plus, pick any type of letter you want, P, where the vector P is negative 2a. And negative 2a is this. So just add these together. So this gives you 8.61 y hat minus 5.135 x hat. So that is the resultant of c minus 2a as a component vector. To switch it into polar, you know that its magnitude is 5.135 in the x, 8.61 in the y. The reference angle looks like this because it's third quadrant. The absolute angle looks like that. So absolute is 180 plus theta r. Theta r inverse tan of, well, whatever these things are in terms of symbols, opposite 8.61 over adjacent 5.135. In fact, this is E, so this would be little e x, little e y, or inverse tan of little e y over little e x. Since I'm only dealing with reference angles, I don't use negative signs in these calculations. 59.2. Because it's 59.2, the absolute angle is 180 plus 59.2, or 239.2. And that's the absolute angle. The magnitude of this, E, is 5.135 squared plus 8.61 squared, just standard Pythagorean theorem. Ooh, and I must have planned ahead. 10.02, yeah. So this E vector is 10.02 newtons per coulomb at 239.2 degrees.
Dr. Ishmael?
Yes.
So how do you know how to draw the triangles? Like how do you compare to the problem you just did, drawing that triangle, compared to the first problem, like with the CX?
Yeah. How? And we answered it. Did you take my 213?
I did not.
Oh, you did not.
I took Dr. Marsh.
Okay. What I need you to do is, and I need to do on Monday, what I'll try to do is post videos of my 213 lectures on vector addition. And I'm a big, huge fan of magnitudes and using logic to determine signs. When I added these two together, the x component was negative and the y component was negative. Therefore, it was a third quadrant vector. What I've been trying to do over the last several years is streamline the entire affair so you try to memorize as few equations as necessary. Vectors, there's the simple vector, the easily convertible vector, which isn't going to happen in this type of game. But the vectors will always break down into one of four quadrants. There's only four quadrants there: first, second, third, and fourth. And when there are many ways to add vectors, but the way that I do it, the streamlined way, is these triangles are always drawn x, then y. X, then y. I call it the vector butterfly. If you draw your triangles like this, where the x is moved first and the y is moved second, then you can always say that the reference angle is the inverse tangent of the y component divided by x. And you can always say that the sine of theta r is the opposite, or y, divided by hypotenuse. And you can always say that the cosine of theta r is always the x component divided by hypotenuse. If you move y than x, it changes the whole thing. It flips things around. So what I remember is that I always draw x then y. And then what I do is I go, well, theta r is inverse tan of y over x, which gives me 59.2. But I know it's a third quadrant angle. Why? Negative, negative. If it was positive, positive first. If it was negative, positive second. If it was positive, negative fourth. But this is negative, negative. So what I have to do is add 180 to the reference angle so I can get that angle right there. The 59 is that. The 239.2 is this. And so that's kind of an abbreviated vector tutorial. But what I'll try to do on Monday is get, I was in the groove on Thursday afternoon. I was really throwing down some knowledge. And then what I realized, I killed Justin Bieber in the first half of the lecture for 213. And then in a fit of, well, I don't have to do anything else, I accidentally tapped the record button and the entire first half of my vector addition lecture was not deleted, worse, never recorded. And so it never happened. So I'm gonna have to redo that part of the lecture. But I have the notes, and what I'll do is, because I know there are people who've never taken my class before, is I'll repost those notes. And on Tuesday for 213, we'll be going heavily into vector addition. So that from very basic first steps. So you may want to look at the video that comes out on Tuesday for that class.
Will that cover component to
Mm-hmm. Yeah, we're gonna do the full thing. Now, granted, they won't be adding electric fields. They'll be adding distances. The units are irrelevant. It's the technique that's important, and that you guys could need. Make sure I didn't tap it. Okay. And now I'm eternally paranoid about my phone. So that's 1 and 2. I'll leave breaking down B and adding D and F up to you. But it's the same, it's lather, rinse, repeat. It's the same thing over and over again. All right, number 3. Two charges are spaced a distance 10 centimeters apart. Stop. So here's our two particles. Here's our distance. And I've declared 10 centimeters to be L. A third charge is placed between the two at the location shown. So that's 1/3 L. This is 2/3 L. All three charges are free to move, but they don't. What are the charges of the other two charges? So, Q1 is given. It is positive 2 microcoulombs. If this is an unknown charge, but it is positive, so Q2 must be greater than 0. So this is a positive charge. That is a positive charge. So the question is, well, first of the many questions, is Q3 a positive or negative charge? What does it have to be, positive or negative? It has to be negative. If that thing was positive, they're all repulsive, so they would all just fly apart. So Q3 must be a negative charge. So we have positive, negative, and positive. And what we have to do is, and this is the fun thing, because I only do this problem twice a year, and when I last did this problem in July, I'm sitting here looking at this problem thinking, really? This is solvable? And of course it's solvable. How can it not be? We've been doing this problem for quite some time. So one of the things that we look at is, well, what did I write? All three are allowed to move, but they don't. Which means that the net force on all three particles is what? 0. So the sum of the forces on 1 is 0. The sum of the forces on 2 is 0. The sum of the forces on 3 is 0. Well, we have a lot of unknowns here. So we got to have something where we can eliminate one of the unknowns. And what I'm going to do is I'm going to sum the forces on 3 and I'm going to sum the forces on, I think 2 would be the right one. So sum the forces on 2. Well, for 2, which is over, might as well do them all 3 in case. Forces on 2, I have minus on plus, so this is plus force on 2 by 1. Oh, I stand corrected. Force of 3, The force on 2 by 3, that force has to be going to the right, so it's positive. So we have K, big Q2, big Q3 over 1/3 L squared. Because Coulomb's law is K, magnitude of the first charge, magnitude of the second charge divided by the distance squared. And this is all equaling 0. And then you have positive, positive, which makes it negative force on 2 by 1. The negative is determined by logic. You know that that's positive, so the force is pushing to the left. It's negative, and so that has to work. So this becomes minus K Q2 Q1 over L squared. Mm-hmm.
Are you just considering any force that moves to the left to be negative?
Yes.
Okay.
We're setting up, thank you, because one of the things that I've been stressing to the 213s is define negative direction, define positive direction. So left is negative, right is positive. Now, one of the things that we could sit here and look at, and fortunately I chose wisely, is in this equation, where this equation is set up, do I need to know what K is? No. Divide both sides by K, the K disappears. I don't even have to know what L squared is. This is 1/9 L squared. That is L squared. Multiply both sides by L squared. They go away. Let me simplify this for a bit, or simplify this a bit. That comes over here, Q2, Q1. equals 9Q2 Q3. And what do we see here? The 1/9 in the denominator, the 9 of a denominator, denominator of a denominator ends up in the numerator.
Why don't you get L squared as the denominator for the force on 2 by 1?
What's the distance between 2 and 1? L. And then the most important thing of this problem is I know for a fact what Q1 is, but I don't know what Q2 or Q3 is. We're doomed, but you can get rid of the Q2s. This is one of the advantages of using the alphabet soup method. Because a lot of times you can't compute it because you just don't know certain things. But quite frequently, you don't need to know them at that particular moment because they just cancel out. So Q1 is 9 times that of Q3, or Q3 is 1/9 of Q1. The magnitude of Q3, therefore, is 2/9 of a microcoulomb. So the charge of 3 is negative 2/9 microcoulomb. And that's solved. Now that you know what Q3 is, you could work on any of the other particles to find out what Q2 is. Let's do forces of some of the forces on Q3. So some of the forces on 3, positive pushing on negative, it's actually a pull. So it is minus the force on 3 by 2. Q1 pulls on Q3 to the right, so it's positive force on 3 by 1, and that is equal to 0. So to draw this in a more simple way, rather than all this garbage to begin with, I'm going to put that over there. Now that the memory of how I did this is coming forth.
Why is 3 force of 3 on 1, 2 on 1?
Oh, whoa, force on...
Wait,
We're summing the forces on particle 3.
okay, sorry. I was thinking 3 was the...
Yeah. So this is the force on 3. No, this is something where it's like a lot of times it's best to say it over and over again so it sinks in. This is the forces on 3. The force on 3 by 2. It's attractive, so the negative charge is going to get pulled to the left. That's why it's negative. The force on 3 by 1, it's a pull because negative positives. It's pulling positive, so it's positive F3, 1. F3, 2 is K, Q3, Q2 over 3 to 2's distance, 2/3 L squared is equal to K, Q3, Q1 over the distance from 3.
Would it not be?
Whoa. Yeah, what did I, 3 to 2, this should be 1/3. That's the correction, correct?
Why is the force on 3 by 1 positive?
Because these are differing charges. So it's a pull. This one is going to pull this one to the right. Forces to the right are positive. This one is going to pull 3 to the left. Forces to the left are negative. That's why there's a negative sign there and a positive sign there.
I was looking at the one all the way on this side as 3. That's why.
Oh, that's okay.
It's like 2, 3, 1.
Mhm.
Okay.
It's just, yeah. So the distance from 3 to 2, there to there, is 1/3 L, 1/3 L squared. The distance from 3 to 1, there to there, is 2/3 L. So 2/3 L squared. Now each of these have a K. Each of these have a Q3. Each of these have an L in the denominator that is also squared. Each of these have a 1/3 squared in the denominator. So simplifying, KQ is equal to Q1 over 4. We now know what Q1 is, and we know what Q3 is, so we could figure out what Q2 is. It's just 2 divided by 4, or 1/2 microcoulomb. Probably the most important phrase in this problem set, or this particular problem, is that sentence right there, which means you know for the fact that the sum of the forces on each of the particles is 0. That one sentence gives you so much power to work with.
That's the answer. Q2 plus Q1 over 4.
Yeah. Well, that's not. If Q1 is 2 microcoulombs and Q2 is just Q1 divided by 4, I leave it to the student to take 2 and divide by 4. I have to give you some challenge.
Where do we find Q1?
If you've read the problem, Q1 is positive 2 microcoulombs.
Could you specify again the difference between the small q and the big Q?
It's something that, it's like I'm trying to think of the word. And it's an English word, so I'm physics. I don't know what it is. I aspire to do this. A goal? If you know English, let me know what this word is. It's something that I always try to do, but if I don't do it, it's okay because it's not really that big of a deal. Q, if I use little q, it could be positive or it could be negative. Big Q is always positive. And Q1, you can just say magnitude of charge.
Is it intent?
It's an intention. I could say, there's a bigger word. There's a, similar to a promise, but not exactly. It's a goal I aspire to. It's an aspiration. I think that may be it. Hey, this is physics. We don't do English right now. So I mostly try, big Q is a positive charge. Little q can be positive or negative. But it's not always. So I'm trying to make it most of the time. Yes?
When you go into this stuff, you just 3, 2, and 3, 1, right? What about this? When do you use 2, 3?
When you've got 2 subscripts for something like this, the first subscript, force on blank due to blank. The first digit that's mentioned is the force that is the object that is experiencing the force. So F sub 3, force on 3. F sub 2, force on 2. The second digit, is the particle causing the force. So when you see F sub 3, 2, the force on 3 by 2. F sub 2, 1, the force on 2 by 1. So that's how it's written and that's how it's stated. Which one do you go with? I don't know. I think you could actually, you could pick any of the three. The force is on 3, the force is on 2, the force is on 1. The technique would be the same, I believe. The K's would cancel, the L squares would cancel, and one of the unknown charges would cancel. Just be sure that Q1 doesn't cancel, because Q1 is the only known charge that you have in the assortment. So it's a weird 2 equation, 2 unknown problem. Or maybe it's a 2 unknown problem because you just don't know the 2 charges. So that's it. All right, 4 is a hateful, spiteful problem. What I'm going to do is I'm going to set up 4, and then you guys can just bash it out. 4 is taking problems 1 to 2 and just being evil. With problem 4, you have 4 charges. And what I'm going to do over here is I'm going to list the charges. Q1, or actually 1, 2, 3, 4. So that'll be in. Q1 is positive 4 microcoulombs. 2 is negative 10 microcoulombs. 3 is positive 7. And 4 is positive 10. X is, for X1, minus 3 and 3. All of these are in millimeters. Negative 8 and negative 3. Positive 5 and positive 1. 0, 0. And actually, what I'm going to do is I'm going to draw it even bigger. So charge 4 is there, and it's positive. Charge 1, negative 3, 1, 2, 3, 1, 2, 3. So there's a positive charge out here. Positive, positive means it repulses, which means the force on 4 by 1 looks like this. Charge 2 is negative 10 microcoulombs, negative 8, negative 3. So 4, 5, 6, 7, 8, 1, 2, 3. So that second charge is out here. It's negative. It pulls the positive charge towards it because they're of different charge polarity. So that force is that way. So the force on 4 by 2 is that. The last one, positive 5 and 1, 1, 2, 3, 4, 5, and 1, so that's here. It is a positive charge. Positive, positive, it repulses, which means that the force on 4 by 3 is out there. This problem is similar to the one that we did in class Tuesday. if not Thursday the week before. I'm guessing Tuesday. So take a look at the lecture notes and videos from the Tuesday of this week, because what we did is we added these E field or these forces together. So the setup. So for the force on 4 by 2, what you do is you go K, Q4, Q2 over R4 to 2 squared. Now Q4 is just the magnitude, so I won't be doing any calculations other than putting in the numbers. Q4 is 10 times 10 to the negative 6. Q2 is 10 times 10 to the negative 6. And then R squared, one of the ways that I made things easy is it started at the origin. So the distance from there to there is the distance in x squared plus the distance in y squared. So for 4 on 2, it's 8 times 10 to the negative 3 squared plus 3 times 10 to the negative 3 squared. And you just write it like that. And why is there no singular number squared? Because x squared plus y squared equals r squared, Pythagorean theorem. So you get the force from this.
Why is it not a negative? The 10.
Coulomb's law states you're calculating the magnitude of the force. So that's why I use, to the person who was asking about it, big Q's. What do big Q's imply? Magnitude or strength, yes. So there are no negative symbols in there. What we've done is we've used logic to say that this force is going to be third quadrant, down and to the left. This will give us a number. I don't know what it is. I don't want to know what it is. But you will get it, and then you will calculate your reference angle, which is that inverse tan of the distance in y, which makes it, we're doing 3 divided by 8. And that will be the reference angle. Why do I not include 10 to the negative 3? Because there's a 10 to the negative 3 in the numerator and the denominator. They cancel. It's irrelevant. And so now what you have here is you have a vector with a force and a reference angle. Force and reference angle. That means that the force on 4 by 2 in the x is 4, 2 cosine theta r. And the force for 2y is F for 2 sine reference angle. Those are the magnitudes of the force components. You now know that this is a third quadrant force. So F for 2 would be minus F for 2x x hat minus F for 2y y hat. And what I've done is I've outlined how to get F for 2 as a vector in component notation. What you do with this is you apply this knowledge in working with F43 and F41, and you will get a table F4, 3 is down and to the left, so it's going to be minus, minus, some number. F4, 1 is fourth quadrant, which means positive, negative. Because it's fourth quadrant, yes. And all you do now is you add. What you're doing now in 214 is exactly what you did in 213 with an extra problem on top. The extra problem is using this and calculating these. But once you get the component, it gets way easier. You add your components together. So this is F4x x hat and F4y y hat. And depending on the signs, my guess you're going to end up with a negative negative, is you rebuild it. You use the Pythagorean theorem to get the magnitude of that side. And you know your components, so you can calculate your reference angle. The reference angle is the inverse tan of y over x. It's third quadrant, so you add 180 to get absolute. And there you go. Number 4 is evil. Number 4 is tedious. Number 4 is like a dozen problems in one thing. Will you get something exactly like this on the test? No, but you will get a watered down version of it on the test. Question, yes?
I think I was copying something else, but where did you get the 8 plus 3 times to the negative third squared? Minus the r squared.
This is the delta. Now really what r squared is in this case is delta. Hold on, let me rephrase this because I want to get this right. Oh, I know exactly what I'm going to do. R squared is delta x squared plus delta y squared.
Oh, is it Pythagorean theorem?
It's Pythagorean theorem. I just substituted the r squared with delta x squared plus delta y squared. That's what I did. Your question.
Yeah, I was wondering where you got the r squared from.
Okay.
Okay, so you take the coordinates from 2.
Now really what I'm doing is I'm calculating the difference from 4 to whatever particle it is. The advantage that I've given to you is that I've put this particle where we're studying at the origin, which means that r squared will always be the change in x over the change of x and change of y, which is really just going to be the absolute value of those coordinates.
So why is it times 10 to the negative third?
Because you're dealing with millimeters. So all the unit coordinates are in millimeters. You have to change them to meters before you plug them in. Yes?
Is it not r squared squared?
No.
Because of the Pythagorean?
No. Would you care to explain, Dr. Eschenberg? I'd love to. The Pythagorean theorem, the thing that we do is we understand that C is the square root of a squared plus b squared. But what happens when you square both sides? C squared is a squared plus b squared. So there is no need to take a square of a square. That's incorrect. So that's really what I kind of did. All right. Now, number 4 is long. Number 4, and actually what I'll say is this, there's solutions of number 4 all over the place. In video form, in notebooks. What I need you to do is go through this problem and understand how to do this. It is long, it is painful. As I've said always before, it is much better to sweat in practice than bleed in combat. So, sweat now, pass later. All right, next, number 5. Gets a lot easier from this. Number 5, 2 charges shown below are attracted to each other, but one is attached to a spring, the other is fixed. When the fixed charge is removed, the charge on the spring moves to the rest position. The image is not to scale. What is the spring constant of the spring? So when it stretches, so this would be the unstretched position. This is the stretched position. There is a change in x. We can consider x to be 0, the rest position. This position x is 0.2 meters. So the force on a spring, or the force on a mass due to a spring, F equals kx. This force must be to the left. If I was doing this as a vector, F vector is negative kx vector, where x is the displacement vector. Really, as if I'm writing F equals kx, x is the distance. The other thing that we have is we have another charge. This is a positive 4 microcoulomb charge. This here is a negative 6 microcoulomb charge. They are opposite charges, so it pulls to the right. So I'll call this force due to the spring, this force due to the charge. The sum of the forces on the particle are 0. Force on the spring is to the left. Force, because of the charge, is to the right. So the force on the spring is equal to the force on the charge. Now the force on the spring is just kx. The distance x multiplied by the spring constant k. The force due to the charges, oh, we got to keep track of this. The force due to the charges is Coulomb's law. We have to be careful because the K here and the K there are not the same. So what I'm going to do is I'm going to write capital K with some lines to make it a little bit different. Q1, Q2 over R squared. I'm looking for the spring constant. So the spring constant K is that charge, Coulomb's law K, Q1, Q2 over XR squared, where these are the magnitudes of the charges. 4 times 10 to the negative 6, 6 times 10 to the negative 6. That X is the distance it extended, or 0.2. That R is the distance from the charge to the other. So this becomes 3 times 10 to the negative 3, and remember to square it. And that's all you do. It's plug and chug from that. So you have to remember Hooke's law, and you have to remember Coulomb's law, and you put them together, and boom, there you go.
What is it, negative F of what?
F sub S, force due to spring. F sub C, force due to charge, or Coulomb's law. Because when the charges were close to each other, when the -6 microcoulomb charge was there, the charge pulled the spring and eventually it got to a point where it was at rest. So that's why when it says, when the fixed charge is removed, the charge on the spring moves to its rest position. So really what you're saying is you've got two charges that are just sitting there, so they're at rest, sum of the forces is 0. You pull it away, and then that +4 moves 0.2 meters to the left to its rest position.
So it's serious because like the spring is pulling this way equally as the charges are pulling that way.
All right. Man, we got a lot of this. So accelerating electron. So I've given it to the class to look up what the charge of an electron is. It's on Wikipedia. There's also the mass of the electron. It's on Wikipedia. Also, for those of you too lazy to go to Wikipedia or too poor to open up a book, electron rest mass is that. I forget. Charge on electron is that. There you go. You can thank me later. So an electron is at rest in electric field shown as at above and at the origin. So we have an electron right there. The E field is pointed to the left at 30 newtons per coulomb. What is this distance x at time equals 30? So it's a combination of charge in an electric field and one-dimensional motion. So x equals x naught plus v naught t. Both are 0 because it started at the origin and it's at rest, and 1/2 at squared. I don't know what a is, but I know Newton's second law, F is equal to ma, and I know that the force on the charge is Q times whatever the electric field is. So A is QE over M. Do some substitution. X is 1/2 QE over M T squared. I know what Q is, charge of an electron. I know what E field is, it's 30. Time, 30 seconds, given. Mass of the electron. Everything is given. 6 is now a plug and chug. There you go. Kind of it is, yes, it is a little offensive. Problem 6 will take about 2 minutes to do, but problem 4 will take about an hour and a half. There you go. I also recommend for number 4, number 1, number 2, I would use a spreadsheet to do all the calculations. Spreadsheets are exact and they're guaranteed to work. Just set up the equations and then just let them run. Because doing everything by hand is just a pain.
So that one right there, is it where you have Q and then big E, is that Q sub little e times?
No, this is the charge of an electron, Q. E is the strength of the electric field, 30 newtons per coulomb.
Okay.
So this is 1.6 times 10 to the negative 17 times 30. I think it is. I don't know. I'm not a botanist. I don't memorize stuff. 10 to the negative 19, yeah. All right, number 7.
The number you just said was for Q or for QE?
No, QE are separate. Q is the charge of the electron. Big E is the electric field strength, or 30. So in the numerator, it would read 1.6 times 10 to the negative 19 times 30 times 30 squared.
So where'd you get the 1.6 times 10 to the negative 19?
It's an electron.
The little q. Oh, okay. It's just.
Yeah. Yes.
Did we do that for 20 and 30 seconds?
Oh, that is a good question. Correction, all the time should be for 30 seconds. So I'm going to get this a lot, and it's amazing that errors like that still sit there waiting. But it's not a... Once again, Eschenberg rules on numbers. I don't like numbers. So if there's an error like that, I'm not sweating it. Number 7, we have a charged particle sitting in an E field that could be either to the left or straight to the right. It is a positive 2 Coulomb charge, and it is at an angle from the vertical at the angle theta, and theta is 30 degrees. So the first question that we can answer is what is the what is the direction of the E field? If there was no E field, that particle would be hanging down only under the influence of gravity. So if the force caused by the E field or created by the E field causes the positive particle to move to the left, in which direction is the E field? Dun, dun, dun. It's to the left. Positive particles feel forces in the blank direction to the E field.
Same direction.
Same direction.
Would that be positive 1 instead of positive 2? Or
It's a positive 2 coulombs. It says so on the... Oh, dang it.
Yeah.
Oh, big deal. It's a number. 2 coulombs. So the charge is positive 2 coulombs. The mass is 1 kilogram. There are only 2 forces acting on this. You have QE pulling to the left, and you have mg pulling down. What we're going to do is it's kind of an interesting play on forces on inclined planes. Now, had I written this correctly, oh dang it, let's just draw it again. So this line is perpendicular to a line where this mass will either move. It will either move slightly in that direction or slightly in that direction. Yes, eventually it curves around, but at an infinitely small change in angle, this particle will either go up this fictitious plane or down the fictitious plane. mg is pulling straight down, QE is pulling straight to the left. This is theta. So if that is theta, there is a geometry question in all of this, then if that's theta, then that must be theta. And if that's theta, then that must be theta. Let me explain why. This angle plus that angle plus 90 degrees is 180. That angle plus that angle is 90. So the way that you can sit there and argue things is that particular angle is 90 minus theta. So if that angle is 90 minus theta, that angle's gotta be theta, with this line and two parallel lines running around. That theta and that theta are the same. This is not geometry class. You can kind of just sit there and wave your hands and say that that angle and that angle are the same. You can also argue with, think about this. As theta gets smaller, this line starts coming down. These two angles will decrease. As theta decreases, those angles decrease. As that angle increases, those angles eventually reach 90 degrees. So those angles are the same. Like I said, this is not geometry class. I'm not interested in the discussion of how you got this to this to this, but just kind of think about it. So because these are thetas, this is QE cosine theta. It's the force of Coulomb's law that's going in this direction. If that is QE and that's theta, and because that is an angle theta and that is right angle, then this has to be QE cosine theta. mg works the same as when you're on an inclined plane. If that's theta and if that's theta and that's 90 degrees, this is theta. And so this becomes mg sine theta. The force down the hill, mg sine theta. You can look at the notes from back when we did objects on inclined planes. And you know this thing is at rest, so the sum of the forces in y is equal to 0. I don't care about the forces in x because the rope is providing the tension against that and that, but those two forces are opposing each other. So this is equal to minus QE cosine theta plus mg sine theta.
And those are the two that you were opposing one another?
Those are the two that are opposing each other.
Why is QE cosine negative?
QE is, when you look at this, it's going to the left. Traditionally, left in my world is negative. Now granted, when the left-handers of the world unite and overthrow everything, left will become positive. But until that time comes, I'll just deal with you guys. So QE cosine theta is equal to mg sine theta. Well, now everything just becomes a case of find E. Mg tan theta over Q. Sine over cosine is tangent. That's the E field.
Why is it the sum of the forces in y? Would it not be sum of the forces in x?
Because I chose my axes weirdly. It should be force in x. Correct. Because when you rotate this, it's like that. So it should, yes, it is correct. It's not a big deal, but in an effort to be consistent with our choices, you are correct. Well, it's still, no, it's still x. It's just, I mean, it could be axis donut. What is donut? Well, donut is the motion in that plane. You could call it anything, but the way that we traditionally use to avoid confusion, x in this horizontal and y in the vertical. Though in reality, it gets a little weird because it's at an angle.
So is the direction still what we determined by logic, the way that the positive charge was moving?
Well, in this case, you did, in a way, yes, I confess my sin. Technically, Q, that little q should be big Q. My defense is, and I was thinking this when I wrote it out, the magnitude of the charge, or the charge itself is positive, so the fact that I used big Q or little q didn't matter. Technically, yeah, that should be a big Q.
If the direction of the electric field was just determined
By the fact that it's a positive charge and the fact that it leaned left.
and it said it's going horizontal.
I defined that the electric field was going horizontal. Oh my goodness, the nightmare that we would have if I put the E field at an angle.
Yeah, that would be terrible.
So thus far, it really doesn't seem like it matters if you use big Q or.
I don't care about big Q or little q. I have a traditional way, the reason why, almost like I'm on a psychiatrist's couch. The reason why I use little q in this case is that I was raised up to think F equals little qe. And that was it back in the day where they were kind of like, Q is just little q is the magnitude of the charge. And there were circumstances where little q was the magnitude, and other times where little q could be negative. And I just adapted. I found, okay, no big deal. Well, okay, that little q is a magnitude. But what I'm trying to do, and it's been taking years to do this, is streamline my knowledge so that it's consistent.
Is there a case where it actually matters if the Q is negative?
It does, I think. But in this case, the whole determination of the E field was based on the fact that I told you that was a positive charge, and that was leaning left. So you used your knowledge of positive charges always get force in the direction of the E field, so that E field must be left. I really work hard to, like at 212, physics 212, you gotta be way more precise, and the equations tend to be a lot more ironclad. In 213, it's a weird mix between 212 and physical science. And with physical science, pretty much all of it is done with logic and rationalizing it out. We're the misfit of the classes. Not pure math, not pure reason. We're in the middle.
Okay, for this one, explaining how you know which way it's going. I know it's a positive 2 coulombs, so that means it's going in the same direction as the
Because
force.
because the charge polarity is positive,
Yeah, it's going the same direction as
it
the
has to go in
force.
the same direction as the E field. Yeah, the force due to the E field.
Okay, and so how you know it's going to the left?
Because it's moving to the left.
Okay.
So it's a positive charge. The E field either goes to the left or right. If it's a positive charge, if the E field was going to the right, it would feel a force to the right and it would swing to the right. But because it's leaning to the left, it obviously is experiencing a force to the left. Using that and the fact that charges feel forces in the same direction as their E field, it has to be to the left. We're only down to 2 problems. Yeah, YouTube's gonna go, what? This is a 2 gigabyte file. What's this all about? Mystery problem number 8. It's a one-dimensional motion problem. You were on a space station. Really what happens is that there is a room. You send a particle in the room. Hold on.
You dropped it.
Oh, okay. Okay, never mind. I was thinking about a different problem. This is exactly like the problem that we worked in here. Look at an earlier lecture, Tuesday, maybe last Thursday. So we've got gravity, we got an E field to the left or right. The charge is positive.
Do you just assume that it's positive when it doesn't have a sign, but it doesn't say anything?
I say charge is 30 nanocoulombs. And this is a good point because I think a valid, if this showed up on a test, I think I would have had the foresight to put a positive sign in front. I think a very valid question is, in a test, is to say to me, is this charge positive or negative? Because it could be ambiguous and I want to be sure. And I would either answer, for that, I would probably answer it's positive. Now, if it had the positive symbol out front and you asked that same question, I would go, it's a correctly constructed problem. They all know what I mean. You will find out what that means shortly. In an effort to remain neutral, if I've done the problem and I know it works, and you're asking me a question, if it doesn't present anything about a correction, I can't answer. I can't answer you're doing it correctly or wrongly. So all I can answer is the validity of the problem itself. And so that's why I say it's a correctly constructed problem. So it does this. So we have y equals y naught plus v naught yt plus 1/2 at squared. It's dropped. I shouldn't cross out y naught unless I do something weird with the origin. My origin I'm going to choose directly beneath the particle before the motion begins. The traditional leftmost, lowermost point. So that means y final is 0. We're using our traditional directions because I'm having flashbacks to when my student asked, well, which way is positive and negative? Down is negative, left is negative, right and up are both positive.
Would the final lineup be 5? So Trevor's 540?
The final y would be 0 because it's resting, or it's on the table. The initial x is 0.
Oh, I'm sorry. Yes, yes.
Mm-hmm. A in this case, AY, now that I have y, is negative 10. Because it's down, the magnitude of gravity is 10. From this, you reorder it so that t is equal to 2y naught over a, y. Oh, and there's a negative sign. So look at the notes. I come up with the same equation, square root of negative 2y naught over ay. Ay is negative 10, the negatives cancel, you get a time. From problem 6, Newton's second law, F equals ma, and force on a particle in an E field, F equals QE. That acceleration is QE over m. This is the time of motion, the time that it takes to fall from there to there. The horizontal force, the force due to the electric field on the charge, had no effect on the vertical motion, only horizontal. So now, negative x is equal to 1/2 QE over y is...
Why do you have x not on the left side of the equal sign equals x plus b naught?
This is one-dimensional motion. The origin is 0. Yes. Am I not? Why am I not seeing this?
Yeah, like why do your x not equal x
Oh.
plus b not x? T.
There should be x equals x naught.
Excuse me. Bad professor.
Okay.
It's only Friday at 4 o'clock in the afternoon.
Just making sure I'm
It should, yeah, we've all thought reality has stopped. So no, x equals x naught. That is 0. And the reason that was causing my brain to fry itself is I know that QE over m and t squared should be a positive number. So why is there a negative sign over there? Because it should be x equals x naught. Yeah, I've only said that equation 50,000 times. Fine, I've got it wrong once. Bad professor. Ugh. So the answer, I mean, really, what I've given you the mass, 300 microcoulombs. Change that into, or micrograms, change that into kilograms. 300 micrograms is 300 times 10 to the negative 6 grams, which means it is 300 times 10 to the negative 9 kilograms. The charge is 30 nanocoulombs, which means it's 30 times 10 to the negative 9 coulombs. Initial velocity is 0. Particle above the ground is 1.4, so 1.4 is 1 naught. X is 5. I'm looking for E. So all you have to do is manipulate that and solve for E. Common algebra. And that's it. That's number 8.
What did you say was 1.4?
1.4 is the initial height, or why not? 5 is the distance that it moved forward, or x.
The 30 times 10 to the negative 9, is that given the coulomb?
Yes, because in bullet 1, the charge is 30 nanocoulombs, so 30 times 10 to the negative 9.
Last question here. Why is it negative 2 under the square root again? For t?
Because when you move, there's some steps that I've skipped. They're in the notes on Tuesday or Thursday, I forget. You move the y naught over, it becomes negative y naught. The 2 comes up, so it becomes negative 2y naught. The ay comes down, which makes it negative 2y naught over a. You square root it, you get that. And that's where it comes from.
And you said
I think it was Tuesday.
Tuesday? Okay, yeah, so just take a look at the Tuesday YouTube video, lecture 3.
with the first bullet is supposed to be micrograms, supposed to convert that to kilograms? Or is it
Yeah, and the way that it's a trap value, because 30 nanocoulombs is converted to coulombs, but 300 micrograms should not be converted to grams and used. It should be converted to kilograms and used. So how I do it to avoid the issue, convert micrograms to grams and then grams to kilograms, and then you're done. All right, last one. Yay, we've gotten to the end. Number 9. This is a game about symmetry. The leftmost particle, or left upper particle, is allowed to move, but it doesn't. All the lengths of this square are the same, and they are of value L. The rules of the game are L is not given. All the charges are fixed, except for big Q up here. that is 6Q, and the value of big Q is positive 4 microcoulombs. Question: what is little q? What is the numerical value of little q? Let's first discuss what's going on in this problem. The upper left charge is not allowed to move. This charge is 6 times 4, or 24 positive microcoulombs, which means this charge is positive 4 microcoulombs. If these two charges weren't here, let's only think about those two. Which direction would this upper left charge go? Up and to the left, correct. So the force of 6Q, or the force on Q by 6Q, is in this direction. I'll just call it 6Q.
Can you explain again how you know it's going up into the north?
Because big Q is positive. 6 times positive is positive, and that must be positive as well, because it's of the value Q. Positive, positive repulse. So this charge must be repulsed away from this. So it gets pushed away.
And that's because Q is positive 4.
Mm-hmm. This one's positive 4, that one's positive 24. Now this is an interesting question. Because of this, and the fact that you know that the upper left charge remains in one position, that it doesn't move, are the little q's positive or negative? They have to be negative. If they're positive, they all repulse the upper left charge, and it just goes on, but it stays. So these must be negative. The main thing about this problem, and this is the lesson, this is a symmetric problem in this direction. If you had a mirror running along this, this would be the mirror image of this. The force on this by that charge is in that direction. The force on this charge by that is in that direction. So what we have here is we have to,
Why aren't the charges, for the positive going towards the negative?
oh, I'm sorry, because I'm an idiot. In fact, so much of an idiot, let me redraw it. Okay, so those are the forces. What I'm going to do is when we add vectors, I'm going to break this vector down into its component parts. It's vertical and it's horizontal. This force must cancel that force, and that force must cancel that force. Why? Because these two are the only ones in the horizontal, and it's not moving horizontally. These two are the only two in the vertically, and it's not moving vertically. So it has to all cancel out. The thing that we have to look at is the fact that the magnitude of this force and that force are equal. Those two charges are the same. The charge being where there's an attempt to move it is the same. The distances from that charge to these two charges are the same. So the magnitude of this is equal to the magnitude of that. Those two are the magnitude of the forces. Since little q is the same as that little q, effectively you're going to get the same number. But I don't give you so many numbers, so we just have to keep them as equations for the moment. Well, let's calculate this force. Well, that force is K big Q 6Q over, if that length is L and that length is L, then this is L squared plus L squared, or 2L squared. And actually square root for the length. But this distance is the square root of 2L squared. So R is the square root of 2L squared. So R squared is back to 2L squared. And we get that. So that's this force right here. This force is this. That force is that. That angle is 45 degrees. It's a line that bisects a right angle. It's a square. So that angle has to be 45 degrees, which means that this angle has to be 45 degrees, which means the green F in the Y is KQ 6Q over 2L squared sine theta. And Fx is KQ 6Q over 2L squared cosine theta. So those are the forces. And the one thing that we know is that that force has to cancel that. This force has to cancel that. Those forces are equal to each other. So those forces must equal to each other. And in fact, you can see sine of 45 degrees, cosine of 45 degrees, you will get the same answer. So we can say that Fy is equal to, if we're going to be consistent with colors, that red F, and Fx will equal blue F. Blue F is the horizontal, red F is the vertical. The equation will look identical. K big Q little q over L squared is equal to K big Q 6Q over 2L squared sine theta. Now it doesn't really matter, sine theta, cosine theta, it's still square root of 2 over 2. But what we're looking at now is the k's cancel. I originally gave this problem to my class during a test, and it was a 212. It was the cal-based. And I was like, there's no calculus in this. It should have been easy for you guys. And they said, it's impossible. And I'm like, oh, really? The big Q's cancel, the L's cancel. They were whining endlessly about how I didn't give them L. But to the students who are new, there are 3 types of numbers. Numbers that you need because you're going to use them. numbers given to you that you need, numbers given or not given to you that you don't need. You didn't need the length of L, so it wasn't given to you. The most diabolical value is the numbers given to you that you don't need. Because if I see you trying to cram a 3 into something and you don't need it, then I understand that you don't understand the problem. So little q is equal to 3 big Q sine of theta. Done. Plug and chug. The rest is elementary. And that's it. It's a combination of symmetry, combination of knowledge of forces, combination of trigonometry, stuff like that. And it's a really good problem. This is one of the reasons why we do tutorial, because it allows me to spend a lot of time doing problems that are a little more involved. Yes?
So Fy equals Fx, right? Because the red F and the blue F are equal to each other?
Yes.
So why did the sign one get to stay in there?
Well, what I did is I chose Fy, which needs the sign, and red F, which is there.
So could you have solved?
So it wouldn't matter if you would have used a cosine either?
Cosine, this is one of the great things. When you see 45 degrees, it should make you happy because sine and cosine is equal to it's the same thing. Yeah. All right, that's it. I'm done. I'm tired. Go home. Play in the yard or something.
If you could do the homework, are you gonna do that?
Huh?
If you could do the homework,
Yeah. You have a good shot at it. All right.
Yeah, was that given?
Done.